Welcome, everybody. Today we are very excited to have Matteo Buschini presenting their paper, Class-Incremental Learning into the Extended Deriverse. Matteo is a PhD student at the University Modena in Reggio Emilia, working on continual learning, among other things. He has very many interesting works recent on continual learning that you should definitely check out. Matteo, we are very excited to hear your talk today. I'm highly confident that the extended Deriverse is going to be a little more successful than the extended DC universe. So without further ado, go ahead and take it away.
Okay, thank you, James. Thank you so much. And so before starting, I want to send a big shout out to my collaborators. So I want to thank Lorenzo Pietroangelo and Professor Simone Calderara. They're my team, and we're doing a lot of work on continual learning. So we've been on this topic for about 3 years now. We're starting to gather, let's say, enough expertise to be very happy about it. And the paper I'm going to present to you today, it's actually an extension of a New Reads 2020 paper we originally published, which was called Dark Experience for General Continual Learning. And this is its extension. So that's for the extended part of the title. And yes, what's the Deriverse? Yeah, you said it right. It's basically our Marvel-like continuity of continual learning works, which focus on replay mostly and knowledge distillation, which is our kind of signature approach. This work is almost published on TPAMI, so I'm happy to present it today because it wouldn't get really the kind of conference-like exposure level otherwise. So without further ado, I'm going to set you up with the outline for today. First thing first, I'm going to discuss the basic work, which is Dark Experience Replay, the basis approach we start from. And then we're going to move on to its limitations, which are the key factor that moved us to do this work. And then we're going to briefly run through the experiments we present in this paper and move on to the analysis. So this paper, if you find it on archive, you'll see it. It's quite massive. It's 16 pages. So we have a lot of very interesting analysis. And so I'm going to present some of them to you today. And I hope you can follow the kind of reasoning we have behind that, and we can discuss it later, of course. So let's start with something which is fairly basic for all of you who are well-versed in continual learning. Whenever we work in continual learning, we have that our network is basically trained on a stream of data that changes in time. The idea is that we have a data set that's split into tasks, which I indicate here with TI. And basically what we want the network to do is to be accurate on all data from all past tasks. So the network is trained on one task at a time, and at the end of it, we want it to be as accurate as possible on all previously seen examples. And that's fairly basic. The problem, of course, is that we do not have the free access to data that belong in past tasks. So basically, whenever we move to task 2, we cannot freely optimize over the data points that were in task 1 and so on. So this is what we want to do, but what we have to do whenever we do continual learning is actually optimize on the data from the current task, which I indicate here with TC, and resort to a somewhat approximate regularizer or regularization term, which I indicate here with LR, whose job is basically to let us help the network remember the past data it's seen in the past. All right. So this is the basic, and there are very many well-known solutions to this problem. Some of the most popular solutions are the experience replay solution. So basically, we have a memory buffer, which I will indicate with M, which is a small space in the memory of our model, which we use to store past data along with their labels. And we simply interleave these examples with the current training data so that the model is able to fit it all and not forget previously seen data distributions. Whereas another approach that we can take is the knowledge distillation-based solution, which is something you see popping up a lot of times in continual learning. There are very important methods that use this, learning without forgetting, iCarl, and all the derivatives of iCarl. There are many. And the basic idea of knowledge distillation, for those of you who are not too familiar with this, is that we have two models. a teacher model and a student model. And basically, the teacher model is an expert on something, and it's transmitting its knowledge to the student model by requiring the student model to mimic its own responses. In the continual learning setting, the teacher model is basically a network fit on a previous task, and the student model is the currently in training network. So whatever with this kind of approaches, you have a previous snapshot of the model which transmits its knowledge to the currently in trained version of the model. And what we did in our initial work, which is called dark experience replay, is basically combining these two approaches. So we basically equip our model with a memory buffer, which stores exemplars along with the original responses provided by the model upon first encountering the corresponding exemplar. So the idea is that we can do this kind of distillation where the model tries to mimic its own past responses. And we do so with mean square error loss. That's a specific case of knowledge distillation. And so basically, this is something which we are very happy about because it's a very easy to implement baseline. But at the same time, it's much stronger than experience replay. We're very happy that it works online. So you don't really need to stop your training and generate a copy of your model to provide you the teaching signal, because the model itself is basically simply recording its past responses and using them as teaching signal in an online manner. And the memory footprint is basically comparable to experience replay because we're just storing some more data in the memory buffer, but that's not where the critical part of memory is, because that's usually associated with the exemplars. All right, so this is the basic primer of dark experience replay, and for the work that I'm presenting today, we started by asking ourselves, what are the limitations of this approach? And the first limitation that we came upon is bias. Now, bias is a pretty well-known factor in continual learning literature, and the idea is that whenever we're fitting a stream of data and replaying data that we've seen previously, we're basically starting a kind of double regime scenario where the model has to fit data that is plentiful and very varied that comes from the current task. So every new batch you see is new data that are very effective in making the model curious, so to say. And at the same time, on the other hand, you have some examples that you're training on which come from your memory buffer, and they are pretty obvious for the model because they're few. They're very easily to overfit. And what happens, we showed it here with this first example I'm showing you today, is that you have a much more significant gradient on the data that comes from the current task when compared to the data that comes from the replay task. So this is, there are a lot of works, as I mentioned up here, that deal with this problem. One of the, of course, most obvious effects is that the prediction of your model will be skewed towards the new classes. So what we show here to you is that basically when we train the model on the second task, so we've seen a first task and then we have a second task, if we consider all the mistakes made by our network and consider where the argmax response was whenever we made a mistake, we see that the argmax almost inevitably lies on the last head, so in the last group of logics you've learned during the last task. So the model, when in doubt, will basically answer with a class prediction from the last group of seen classes. All right. So we have a polarization of prediction. The solution for this is a pretty well-studied problem in literature. So we basically implemented a solution that other groups have come up with recently, is applying a separated softmax or separated cross-entropy layer. What this means is basically we're going to isolate the way our model learns about current task data and previous task data by simply basically masking out all logics that correspond to past classes whenever we fit data from the current task, and vice versa, isolating the logics from the current task whenever we fit data from our memory buffer. Okay, so this now introduces a problem because we have a model that basically is capable of doing classification for current data and classification for past data, but not necessarily able to kind of blend the two. So whenever we do the knowledge distillation loss that we did originally in dark experience replay, we basically apply it to all heads at the same time, so as to kind of have a reconciliation term. This is for the first problem that we saw in there and fixed. Moving on, we have a second limitation, which is kind of subtler, so I need your patience here. And we have to introduce some nomenclature first. So the idea is, try to follow me. Whenever we find ourselves at task TC, okay, so we are in the midst of our training, we see new examples. These examples basically belong to a class whose group of logic we denote as present, okay? So we've basically trained on, I don't know, 4 past tasks. Now we move on to the 5th, and this 5th task may include, for instance, I don't know, 10 classes. This group of 10 logics that corresponds to these 10 classes actually make up the present of the model. We call it that way. At the same time, we have a past space in the prediction of the model that encompasses all the logics of classes that came before. So whenever we do knowledge distillation, these logics are kind of important because their activation, even though we know that the correct logics to be predicted for the class at end is going to be among the present ones, past logics kind of encode with their activation whether the example we see is similar to a class we have already learned in a past task. So we're very interested in seeing how much they activate, and this is an important factor in knowledge distillation. And then we also have a group of future logics. The future logics are logics that we instantiate at the beginning of training, but they are not yet used because they basically are going to encode the logics for classes that are still to come. We have not seen them yet, okay? So this is what happens when we examine an example at task C. Now, if you followed me when I was talking about dark experience replay, you know that it is a replay method. So say now that we are going to forward through the model an example which we originally inserted in the memory buffer at task C tilde, which came before task C. Okay, so this is an example from the past we're replaying while the model is learning task C. What we have here is that the knowledge distillation target we have for this example, which is basically the original response of the model, will be quite comprehensive as concerns the logics of its present, okay, so the similarity with other classes that were learned in task C tilde. It's going to be very interesting for the past portion of this example, so all the logics that encoded the similarity we have with classes that came before C tilde against this example, which is learning C tilde. But at the same time, it will be composed by a series of future logics that encompass all the section I'm highlighting here, which will have no meaning at all. Because whenever we first met this example and inserted it into the memory buffer, we had no way to basically tell what these future logics were supposed to encode. Well, now the model has grown. It's been trained on 2 more tasks. So we can kind of assume that the response it provides for these 2 tasks here, so task C and task, say, C-1, is actually significant. So we shouldn't match this with the responses we previously gave, because that's basically like damping it down and saying, no, you're getting it wrong. This is not similar to a class you're seeing in task C. It's nothing because the future logics contained no information. This group of logics, we call it the logics of future paths. So the idea is that they were future logics when we first inserted the model into the memory buffer, but since then they've grown to encode significant things which we haven't captured in our distillation objective that comes from our memory buffer. So once again, whenever you do replay the way dark experience replay works, you're basically asking the model to match future logics which are just useless. They don't encode anything. But what's even worse, whenever you replay logics for classes which were in the future but are now being learned by the model, you're basically just requiring the model to dampen the original, the response it can give, which could attest to some similarity between classes learned here in task C or C-1 against the task, the class we've seen in the past. All right. I'll just stop it a second to tell you that this is not a problem if you do knowledge distillation the way iCarl or learning without forgetting work. These models, basically, they will detach a copy of your model and use that to provide a teaching signal to the online learner. This means that they can basically, they don't have a blind spot towards this, because they can tell you how an example from the current task looks to them and how similar it looks to their classes they know. This is not possible with there, because we are basically part of the target space, which is just not ready to be distilled. I understand this is kind of complex. I hope that I can clarify it to you with a couple of quantitative examples. So what we do here is we have our model, DAR++, in a version which we indicate here with ACE, which already corrects for the bias problem I talked about in limitation 1. We trained this model on CIFAR 100, which is a very well-known image classification dataset. And after completing its training, we're going to see what is the average activation we get for the examples in class 50, which is mouse in CIFAR 100. All right. So if we measure the average response we get from the logits of the model, and of course ignore the one that corresponds to mouse, which should be around here, and which would be, of course, the maximum we get, but all other logits, which kind of encode how mouse looks similar to other classes we've seen on the stream, are distributed like I'm showing you here. So what can you notice about this? You can notice that there is a big emphasis on logits we've seen previous to learning about mice. And on the contrary, there is very little energy lying here in the classes that come after we've learned mice. So basically, the model is able to tell whether a mouse is similar to something we've seen before in previous tasks, but not if a mouse is similar to something we're going to see later on. All right. I know this is complex, so I have one more example to show you what I mean with this effect. We're doing the same thing which I was telling you about a second ago. So we have a model trained on the whole CIFAR 100, and then we're going to see what kind of similarity we can see in the activation of the non-maximum logit for it. Let's consider first the response that's given by a joint training model. So the upper bound we have in continual learning, which is no continual learning at all, so learning all classes at the same time. If we simply train a model on CIFAR 100, we get this kind of responses. So we see that mouse is kind of similar to this class here, which is hamster. It's pretty reasonable, or possumus is, or rabbits, or shoes, or squirrels. So what we see here is that the non-maximum, so once again, I've removed from this illustration the logit that corresponds to mouse, and we see that the non-maximum logits kind of encode the interesting fact that there are other classes in CIFAR 100 which are similar to the class mouse, okay? Now, let's do the same with dark experience replay, and we can see that basically, among these classes which the joint training tells us are the most similar to mouse, the model is kind of able to grasp that a mouse kind of looks like a hamster, possum, or rabbit, but fails at telling you that a mouse is similar to a shoe or squirrel. Now we're in continual learning, so we're learning classes along this timeline here, starting from the first one here to the last one. We're doing it in AZ order, in alphabetical order. And so basically, we can only account for this similarity when they are before us or just right after we've learned mouse, but not if they come some couple of tasks after that. To show you that this is real, we try and train the same models, DAR++, in reversed class order. So now we start from the class in CIFAR 10, in CIFAR 100 that commences with a Z, and then move back up to the first class we have that starts with an A. If you see, and we plot you the activation here in the opposite world, what you see here is that this model is kind of able to grasp that a mouse is similar to a shoe or a squirrel, but fails at telling you that a mouse is similar to a rabbit, a possum, or a hamster. So we basically have a problem here. Okay, I hope I convinced you. Interclass similarities, which are the core of what happens in knowledge distillation, the informative pattern that we want to learn, Well, they depend on the learning order for the dataset. All right. So this is a major hindering factor. I'm going to present you with a spoiler of what we're going to do next. We're going to present an extension of Doc Experience Replay, which kind of fixes this effect. So you can already see here that we get better responses that account for an activation pattern that's closer to the one of the joint training. All right. Whenever you train it either in forward or reverse order. So this was the problem. The solution to this problem is twofold. The first half is we basically update the logics we have in our memory buffer. So once again, Doc Experience Replay stores example in the memory buffer along with the original response that was given by the network. Whenever we consider the part of these responses that are logics which the network has not yet seen, we recognize that the model which responds in the future tasks will be more expert on these classes with respect to the original teacher when it learned the example first. So we're simply basically saying whenever you are considering logics that will come after, just update them if you happen to replay them later. All right. So we're going to update these logics and let the student model have their say on what the similarities are between past classes and new classes we see here in the future. And the second half of the solution we devise is future preparation. So since we have future logics and they do not encode anything, they're useless, as I told you a moment ago, we're going to use them for something useful. So what that is we're going to use them as the basically the leverage for implementing a supervised contrastive learning loss. So we're going to use this portion of the network response to learn whether two examples are the same or not. We use the very well-known subcon approach, where we take the examples we want to replay, we basically perform two strong data augmentation on them so they don't look too much alike. We forward them to the network and require that the future part of the response of the network is the same for both augmentations. And by doing so, we hope that the model is kind of able to grasp what makes these two examples the same. Okay? All right. So with all the pieces I've given you so far, we can provide an overall formulation of the model, and which is the one depicted here. So basically, you have current task data and replay data. Replay data comprises examples, labels, and past logics. Current task data is only learned in the present head, so we do not train past heads with the cross entropy that's used to fit current data. Conversely, the past data is only trained on past heads. And then we have something more. We have a distillation loss, which embraces whole heads for replay examples, which I told you kind of acts as a reconciliation loss term. Future past logics, so logics which were not available when we first stored this piece of our memory buffer, but have become available since, will be subject to memory update so that they can be used in a more effective manner. And finally, for the logics which still have not been used by the model because they refer to future tasks, we're going to do some future preparation loss. So basically, apply this contrastive term to try and learn something instead of use them for nothing. And finally, we also have to include a kind of trickery past-future constraint loss that basically requires that the activation of these logics, which are just unbound from anything else the network has seen so far, we have to require that they don't overshoot the actual logics from other classes. But that's just a small requirement we have to introduce because they are basically separated from all the other things that the network is learning. So this is formalized in the formula down here. So X there, which is the extended version of there, is basically the original there, plus this separated cross-entropy loss, which is to say, examples from the current task are learned in isolation, examples from the past tasks are learned in isolation, plus a loss that refers to the future, which basically encompasses doing this feature preparation last term, which in our main proposal is a supervised contrastive loss, and applying this small constraint I just described to you to prevent overshooting and keep logits well behaved. Okay, so this covers the kind of proposal part of our paper. I'm going to walk you real quick through the experiments we present. We do experiments in the class incremental benchmark, so we're basically requiring that the model must be able to predict all past classes at the same time in a sensible manner. We ran experiments on two very popular image classification datasets, Cypher 100 and Mini ImageNet, and also experimented with a different classification dataset, which is NTU60, which is a skeletal action recognition dataset, which we split into tasks in a typical continual fashion. So these things here are done with convolutional neural networks, whereas NTU must be fit with a graph convolutional neural network. So we also wanted to see whether these models were able to perform with a drastically different network architecture. And what we see here is that XDR is quite effective. It's a very strong performer in all the datasets we've experimented with. And with the second best typically being either DER++, which was our previous proposal, or ICARL and Illuser, which are particularly effective whenever we are in a low data regime. Okay, I don't want to run too much into details for the experiments here, but if you have doubts, we can discuss them later in the question time. What I really wanted to talk to you about today is the analysis part of our paper. So we basically took this extension as an excuse to do some specific study into several aspects of continual learning that fascinate us. And today I'm going to present three to you. The first one is a discussion on the quality of distillation teachers. So basically, we're going to investigate why knowledge distillation is effective in continual learning. And the second point we're going to discuss is an analysis of the geometry of the loss landscape of models and why it matters in continual learning. And finally, if we still have time, I'm also going to show you some visualization about what is forgotten by our models. So for the first point, which is the quality of distillation teacher, we basically met this very interesting paper by Menon et al. And published at ICML 21, which is a theoretical study into the basics of knowledge distillation. And basically what it says is that whenever we're trying to solve a classification problem, we're faced with a reality where every object we want to classify bears a specific degree of resemblance to different classes we're interested about. So if we are trying to, I don't know, classify bottles and dogs and horses, you can tell that the ground truth classification signal, the ideal classification signal that we want to have is that maybe a dog is closer to a horse, somewhat more similar, than to a bottle, which literally brings no resemblance to it. The idea is that we are interested in this ideal true bias class probability distribution, and this is much more nuanced than what we get with cross entropy. If you train a network in the typical fashion with cross entropy with one hot target, what you get is a kind of black and white situation where you cannot really tell about the different nuances and degrees of similarity that there exist among the classes you want to classify. And instead, distillation, which I recall again, is matching teacher signal for a teacher response to the network you want to train. This has the potential to be something much more nuanced and capable of carrying all this kind of secondary information. So to stress this effect, we ran a preliminary experiment, which was very interesting, working with Cypher 100 once again. If you know this dataset, you know that it's composed of 100 classes, but it also has a course level labeling. of 20 superclasses. So basically, in each group of 5 classes belongs to the same superclass. So by assuming that this class should be more similar to each other than classes from different superclasses, we ran this experiment where we test 2 interesting effects on fully trained continual models. The first metric we care about is this secondary superclass error. So basically, we let the model give us a prediction for this example we present. We suppress the ground truth logit and consider where the second argmax response lies. We're happy if it lies in one of the classes that belong to the same superclass. This means that the model has some kind of principled approach where its second best response is still within the same superclass. And similarly, we also have another metric here, which is the secondary superclass negative log likelihood, which basically simply means we're going to use all the prediction logits from the model that belong to the same superclass as a kind of comprehensive signal that accounts for the likelihood of the superclass itself. And we're going to see how it fits in terms of negative log likelihood. So what we see here, which is very interesting, is that if we train our model with standard cross entropy as ER or ER H2, we get lower metrics. Okay. The situation gets better if we use there or there++, which actually apply knowledge distillation. But as I told you before in the second limitation, this kind of dark knowledge that we are encoding, these secondary similarities, only refer for classes learned at task C with respect to classes that we've learned in previous tasks. So this is a kind of halfway knowledge distillation. The metrics for methods that actually detach a copy of the model and use that as a teacher are better because they can account for similarity with the future and the past, and that's the case of Lucy and iCarl. And eXtend, we're very happy about it, gets very good metrics, which are much closer to these 2 models and well above the ones of there and there++. We ran a kind of counter experiment and removed the memory update part from our eXtend loss formulation. So now we're not updating anymore, and hence eXtend is blind towards the future past similarities. And we get back, as you can see here, 2 metrics which are much closer to the ones of there and there++ than the ones of Lucid and iCarl. So the future past information is real, is a real part of the response we want to get from our model. And a second experiment we can use to show the same effect is basically simply training a model on Cypher 100 or Minim agent or whatever, and taking its memory buffer at the end of training and using that to retrain a new model, which if you know recent continual learning literature is basically what GDAM does. If you only train with labels, so with black and white targets, which is what GDAM does, you get a certain level of accuracy. If you use there++ logits along with them, you get an increase in accuracy, especially if you use both. And finally, if you use the logits that come from eXtend so that we compensate for this lacking future past situation, you get the best possible accuracy you can get. So this is also very interesting. Once again, here we're training a model from scratch based only on a small memory buffer of exemplars that we've collected along the way while training. All right. Now, this was for the first part of the analysis I wanted to present to you today. And the second point is the geometry of the local minimum. So now, since the dawn of modern continual learning, there is a very strong emphasis on obtaining flat minimizers for our neural networks. Here I actually stolen a picture from elastic way consolidation, which is one of the first modern continual learning papers. And this paper was already pretty clear into showing you that this was an important factor. What it shows here is that you're going to train your model on 2 tasks, task A and task B. Now, if the parameter configuration that solves task A lies in this region here, which is far away from the low error region for the second task, these two solutions are not going to talk. What you're interested in when you're doing continual learning is finding something that lies around here, so having a configuration of parameters that suits task A as well as task B. And this is simplified if you basically devise your loss function to be very smooth so as to allow for as much overlap as possible among your tasks, okay? Now, there are a lot of intuitive explanations as to why this is an interesting effect, but we didn't really find many quantitative experiments that proved this, the importance of this factor. So to provide a better intuition, we actually ran a quantitative experiment, which was pretty interesting. We're going to train a model on pairs of tasks, so task 1 and 2, or task 2 or 3, or 3 and 4, and so on from, again, it's cipher 100. And the idea is that we're going to train on the first task in different configurations that I'm going to go through in a second, and then train on a second task performing experience replay so as not to forget the previous task. And we measure the final accuracy for the first task we've learned. Now, we can do this in three ways in our experiments. We can simply apply cross-entropy to learn the first task. So that's basically just stochastic gradient descent, the plainest way to do it. Or we can experiment with loss terms, which are called LFR and LLR, which are flatness and linearity regularizers. What they do basically is they do devise an adversarial loss term to require that your gradient be flat or at least linear. In other way, they basically enforce by design your loss landscape to be quite flat. And we see here in this radar plot, you see compare the accuracy of the base model in gray and the accuracy of the model that does its first task with this regularizer in color, that there is a dramatic improve in accuracy, and specifically in the retention of the accuracy of the first task, if we actually took extra care to have a smooth loss in the first task. So we were pretty satisfied with this result because it's the kind of illustration of an effect that's pretty clear in literature. And basically it says you should always strive to have flat local minima. So after this, we basically worked on some experiments we ran in our original dark experience replay paper, which kind of test how flat our loss function is. And we can do this in two ways, either by, and this is the plot on the left, basically perturbing the parameter configuration of the model. So we have a fully trained model on a data set and start to add random noise to its parameters and see how resistant the model is to this kind of perturbation. So models that still retain a lower loss function in the face of higher perturbations, as shown here, they kind of reach a better overall loss minimizer, which is flatter because it's not easily perturbated. And we see here that dark experience replay and extended dark experience replay, they're basically flatter in the loss function with respect to experience replay or experience replay with the correction for the bias. Another way to test it, to test this same effect, is measuring the eigenvalues of the Hessian of the loss function at the final minima attained by the model. And once again, lower eigenvalues denote that the loss landscape is less curved. Okay, so finally, for the last piece of analysis that I'm presenting to you today, we're going to go through some visual explanations of what the model forgets. We were inspired by this very nice paper from Ebrahimi et al. At ICLR 21, which was called Remembering for the Right Reasons, and basically showed that continual learning models are capable of still performing rather good, but not being accountable as to why they are making the right prediction. So what we did here is we took a data set, which is CAB 200, which is a data set that simply contains classes of birds, which is interesting because it has segmentation maps. So by using it on a continual learning model, we can then see where the reason for the prediction made by the model lies by using GradCam or some other kind of activation map, and try and test whether this network activation overlaps with the ground truth segmentation map we're provided. So what we were able to see by doing this is that, on average, eXtended DER is better capable of retaining an activation map that overlaps with the ground truth segmentation map whenever you replay past data. Whereas if you consider what happens with experience replay up here, experience replay kind of, you see, has a pretty nice map when it first learns this example, which is an example from task 0. And then as you move on to later tasks, the kind of reason for the prediction that it provides drifts away to, let's say, non-salient spots in the image. This is an interesting example that accounts for the capability of providing sensible predictions for the argmax class. We also tried and ran a hybrid experiment, which kind of intertwines this insight with the topic of secondary knowledge that I've discussed before. And the idea is that to do this, we needed a data set with segmentation map with more than one label per image. And the way we constructed this was we combined two data sets, Cypher 100 and COCO. We found that these two data sets have a shared subset of classes. So basically, there are 8 classes which are present in both. And we basically devised this very funny data set that's constructed by stitching parts of COCO images which are provided with segmentation maps on top of Cypher 100 image. So here you have, for instance, an image that has a primary label, which is couch, and a secondary label, which is bear, or here a chair with an orange. And what we wanted to see is whether a fully trained continual learning model is capable, once again, doing the investigating its activation map, it's able to account for the prediction of the non-maximum logic it's producing with respect to these non-maxima classes. So what we've seen here is that, once again, the models that do knowledge distillation, such as dark experience replay and eXtended, are much more effective than experience replay in telling you that at the end of training, the logic that, for instance, corresponds to a bear, which is the non-maximum class in this example, still is localized above the correct area of the image. So let's say predicting for the right reasons, not only on maximum classes, but also on secondary classes. All right. So this covers pretty much everything I wanted to talk to you about with respect to eXtended, and I hope you will have questions very soon. If you're interested in the paper, you can find it either on the PAMI website, because it's an open access dataset, an open access paper, or on arXiv, of course. And the code for this paper is also available, and it's distributed along with our continual learning framework, which is called Mammoth, and you can find it here on this repo. Before giving you some time to ask questions, I wanted to, James recommended that I present some of the works we have upcoming at the next conferences. This has been a very good year for us. So we have some more pieces of the Derverse that are coming out in a few months. And the first thing I want to tease to you is Transfer Without Forgetting. This is a paper we are presenting at ECCV later next month, and you'll find me in Tel Aviv discussing this. The main topic of this paper is basically pre-training. Pre-training is a very important topic in real-world machine learning, of course. Whenever you deploy a model, you basically want it to be as accurate as possible, so pre-training it's just common practice. And this is also common practice in continual learning to some extent, although we notice that something can happen to the pre-training of your model. And in other words, just like the model is subject to catastrophic forgetting for the classes it learns earlier in the data stream, this kind of forgetting also affects the kind of pre-training features that you have at the beginning of the training procedure. So if you pre-train your model on ImageAgent, say, ImageAgent would be very effective in helping you learn the first classes you encounter, but less and less effective as you move to the latter part of your continual learning stream. So if you want to hear about it and find the solution we propose for this problem, you can check it out on arXiv or meet us directly at Tel Aviv in ACCV. And finally, we also have one last paper coming out later this year at New Rips, which is basically focused on the effect of having a very small buffer when you do experience replay. Rehearsal methods tend to overfit the examples you have in your memory buffer because, as I told you before, they're few, they're not very varied, and easily overfit. So what we saw is that the decision boundary that you come up with for your model when first learning a task gets inexorably deteriorated in time as you can only optimize over this very reduced pool of examples. And what we propose in this work, which will be presented by Lorenzo in New Orleans, is a regularizer based on Lipschitz continuity that basically kind of mitigates this effect and gives you the freedom to have a small memory buffer without overfitting it too much. This is a very cool paper. It's still not on arXiv. It's going to be soon in a couple of weeks or so. And it's going to feature some pretty interesting analysis here too. So this is a first teaser of the buffer guessing game, which is an ablation you can find in a paper and one of my personal favorites. Okay, so I hope I wasn't too long. I tried to keep it as lean as possible. I want to thank you all for the attention, and if you have any questions, please just fire ahead.
Oh, that was perfect timing. Thank you so much. If anybody on Teams has a question, I saw there was a hand raised earlier. Feel free to unmute and ask your question now. There was one question from YouTube Live. Manuel says, "Thank you very much for the presentation. I found your proposal very interesting. Can you explain further the impact of contrastive divergence for eXtend?"
Contrastive divergence? Oh, okay. I'm not really sure. Okay, the only time I used the word contrastive was for the contrastive learning part of it. So I think you referred to that, but if you're not referring to that, just stop me. So basically what I told you is that, let me find the right slide here. Whenever we do dark experience replay, we first encounter an example, store the response the network has given us for this example, and replay them later in the stream. And the idea is that part of these responses are actually pretty interesting and meaningful and convey information to the model that must not forget about this data in the future. But part of these responses, and specifically the ones that refer to logic that we've still not seen, are not significant at all. So we're just filling this part of the response of the model with a separate kind of learning approach, which is a contrastive learning loss. So the idea is that in a contrastive learning scenario, you basically learn how to, you basically learn representation actually, by taking an example, having more than one strong augmented version of it, and requiring that your model learns that they are still the same example. And we do this here, but instead of leveraging a full network response as you would do in a purely contrastive learning model, we're just using this as a fill-in for the part of our responses that would otherwise go unused. So we're just like attaching a bonus learning signal here that is not using, no, it's actually using labels because it's supervised, but the idea is that the same exemplar must be such that the network responds the same way, and this has to be true also for the elements in the same class to some degree. If you're interested in that, I strongly recommend you to check out the literature in this field because it's booming right now. It's very interesting, and this paper I pointed here, it's a good starting point. So if you want to check it out, it's supervised contrastive learning.
Awesome.
I hope that was the question.
Yeah, they clarified that did mean the contrastive loss. So
Okay, okay,
I'll get in a
great.
follow-up question. I am also interested in the part of retraining the flatness for local minima. Is Exter sufficient to guarantee flatness, or could it be also combined with other regularization losses?
Okay. So, okay, what we do with flatness is we measure it a posteriori, so after the fact. And we've seen from from experiments here that XR actually has a flatter final minimizer with respect to other solutions such as experience replay or basic guitar. And so yes, I think I guess the response to your question is yes, to some degree that's sufficient. But of course, you can also come up with regularization terms that specifically solve for this problem. And this is kind of similar to the paper we are presenting at New Rips, kind of. Of course, this kind of losses sometimes tend to be quite intensive because they reason on the kind of shape you get from your gradients, so they might be second degree or something like that. So it might not be very easy, but in general, let's say that a lot of the continual learning literature kind of agrees that having flat minima is a pretty important point. So that's why we ran an experiment to test that.
Great. I think Adia, you can unmute and ask your question.
Yes, thank you. I have a question on slide 21.
21. All right, you kept the number. You're great. Let me see. All right, here we go. 21.
Right. So here, when you explain this memory update and you're doing memory update for only the partial logits, and so my question is, what if we update the memory for all the logits? Now that
Okay.
we've seen the future examples and we get new logits, why don't we update all of them?
That's okay. That's a very good point. So basically, the idea behind the original work was that we did not want to have an updated target here. We just wanted our network to behave as good as the first time you've learned that specific class, because that we say is the best point where your knowledge about this class is richer and the fullest, because you are fitting the stream, which is a much more comprehensive source for learning. But of course, this does not apply to the future past part of the logits, and that's why we update them. If we were to also update the logits that refer to previous data, what I think might happen is that you might find that your model basically deteriorates concerning the accuracy you get from these logits. This happens because the kind of learning signal that you get from the logits when you first saw a class, it's very reliable. It's very reliable because you have learned this class from the stream. You've seen many different examples of this class, and so you're pretty confident that this is a good prediction as to what the logits should be. But this is not true for the future past portion of peer apply for the reason I went on discussing before. So because you still have no clue about what this logits should encode. So we just replace this part of the answer. I fear if you just let the model basically teach itself what the correct level are for these logits, you might run the risk of starting to emphasize the new classes you've seen on the stream and start dampening or forgetting, of course, the previous part of your response. So we don't touch them because we got them at the best possible time in our stream and don't want to decay.
Makes sense. Can I also ask a quick follow-up? So
Yeah.
these experiments seems like they were done with a fixed large head where you assume that this is the maximum number of classes you have.
Yeah.
What if I were in a setting where I keep, this open set classification where I keep expanding my head?
Yeah, that's a very good point because this is the way we work, and we worked for there originally. So and many works don't do that. So if you check out the paper, you can find some experiments I didn't went through today which cover this aspect. And in particular, you have this one where we basically tried to have a fixed number of pre-allocated heads. And so basically we show that the very good effects are obtained even if you just assume that you have like all the heads you need so far plus 2 more or plus 3 more. So you have like a fixed buffer of future heads ready there to provide the additional learning signal you desire. So it's not really, we're not really bounded to the design choice to instantiate all the heads at the beginning. You can also say I instantiate a fixed number or some spare heads in advance and keep growing as I go. So yeah, I point you out to the one of the sections I couldn't go through today.
Actually, can I also ask you? I'm still a little confused because if I have an expanding head, I have a single expanding head, wouldn't my logits computation get messed up when I expand the head, add more classes?
Well, whenever you expand the head, you basically still have the. If you only grow your head, so if your number of logits only grows in time, all you've learned so far, which refers to past logits, is still applicable, and you can still distill it. The novel part, which is the one that refers to the future, gets learned in time. So I don't see really how that could mess up your prediction. I'm assuming that your head is like, I don't know, 10 classes after the first class, after the first task, and then you see 10 more in the second task. So before starting it, you let it grow to 20. Let's say the first 10 logits in your head still encode the same thing that the previous shorter head did. So it's just, I think, a matter of matching, really.
But don't I need renormalize to 20?
Renormalize. Yes. Well, and with logits, okay, maybe this is the point. Whenever I talk logits in doc experience play, we talk about pre-normalization logits. So they are not processed through the softmax yet. They're pre-softmax. This is an experiment in the original paper that you can check out. We chose to go with the pre-softmax logits because they are actually richer and encode more information with respect to what you would get after a softmax, because a softmax kind of reduces the amount of information you have in your network. So yeah, so that's why we don't have this problem.
Thank you. Got it.
Okay, no problem.
Okay. Are there any more questions? By the way, Emmanuel from YouTube Live just wanted to thank you for clarifying everything earlier from the questions earlier. Yeah. So actually, you stole my questions. So if there are no more questions, I think this could be a good time to wrap up. Yeah. Okay.
Yep, that works for me. So thank you all for your attention, for the questions. They were great. And so hopefully I'll see you around in conferences, because this is actually the first conferences I go to, even though I've been in my PhD at the third year because of COVID. So yeah, so actually Tel Aviv will be my first conference. So I hope I meet you all there, or whoever can attend.
Thank you.
Yeah, thank you so much for all of this, Matteo. For all watching now, you can join us next week at the same time, same place. We'll be looking at multimodal continual learning of vision and language models. This will be from Tejas Srinivasan. So see you next week if you want to learn about continual learning of vision and language models together. Okay. Thank you.
Thank you again.